All right. Okay, so today we're going to go over two different things. The first thing is going to be bioenergetics of exercise and training. This is going to lead into one of the next concepts that we actually started talking about, which is specificity. Specificity basically deals with a transfer of training. So our training should mimic what we want to actually get good at. And because your body relies on different energy systems, depending on the intensity and duration of specific exercises, what energy system you use for whatever you want to get good at is going to be important for that principle of specificity. So let's start out with why would anybody train? This image right here is a little bit more in the athletic realm. So what do athletes need? Athletes need, depending on the sport that they're in, either endurance, speed, or strength. And a lot of times it's more on a continuum. So if you look at a football player, they probably need much more, somewhere in the middle of speed and strength. They don't really need endurance. But if you looked at a marathon runner, for example, they would fall almost entirely on the endurance spectrum. Whereas maybe a wrestler would be a little bit different, where they would need strength and endurance. So maybe something like that, strength, endurance, along with a little bit of power. So depending on what you want to actually train for, there's going to be different demands that you need to put on your body in order to actually get good at it. General training goals that a lot of people have. So when we stretch outside of just the athletic realm, it would be increased muscle size. So people want to experience muscle hypertrophy. They want to get bigger muscles. They want to increase their muscular strength, increase muscular endurance. They want to lose body fat, or generally speaking, they want to improve athleticism. And when I say that, that might even be someone who is 50 years old who wants to be able to continue to jump or be explosive and powerful. So that's what I think of when I think of improve athleticism. So generally speaking, most people are going to have some kind of goal like this, and our training needs to be specific to that person's goal. So if somebody said, I want to improve my muscular strength, telling them to go out and row for 4 miles is not going to be conducive to what that person's goal is. That would be violating the principle of specificity. Similarly, if someone wanted to improve their muscle size, I wouldn't put them on a muscular endurance program. So again, that would be a violation of specificity. So today what we're going to cover is the role of adenosine triphosphate, which is ATP. We're going to talk about the 3 basic energy systems, fatigue and recovery, and then the metabolic specificity of training. And then after that, we'll start getting into some of the hands-on things. What do you need to know to design a program? So what's bioenergetics? Bioenergetics is the flow of energy in a biological system. And it concerns the conversion of macronutrients. So macronutrients are like carbs, fats, and proteins into biologically usable forms of energy. So you'll see that we need to break these things down to use them for energy. And energy is the ability or capacity to perform work. So that's energy. So if we're breaking these things down, if we're breaking down things like proteins, fats, and carbohydrates, what is that called? So the breakdown of large molecules into smaller molecules. So for example, proteins break down into amino acids, carbohydrates break down into glucose, fats break down into triglycerides. This is associated with the release of energy, and it's called catabolism. Okay, it's also what is called an exergonic reaction. So an exergonic reaction is energy releasing reactions. On the other side of the coin, the synthesis of larger molecules from smaller molecules can be accomplished using the energy released from those catabolic reactions. So this is called anabolism. So when so if amino acids build up to actually form protein, this is how we get bigger muscles. Amino acids build up to form protein. And this is called an endergonic reaction. and these require energy and include anabolic processes and the contraction of muscle. So this is what this essentially looks like. On the top one, what's an anabolic reaction, or again, what's called an endergonic reaction? If small molecules are assembled to form larger molecules, they need energy. So if I had all of these protein breaks down into amino acids. Similarly, with energy, amino acids can be synthesized into protein. So that'd be the right-hand side of the equation. And then catabolic reactions are when things break down. Catabolic is things break down. So exergonic reactions too. Large molecules are broken down into smaller molecules and energy is released. Okay. So what's the sum total of all of this? The sum total of all this is called metabolism. So metabolism is the total of all the catabolic or exergonic and anabolic or endergonic reactions used in a biological system. So that's what metabolism is. And energy derived from catabolic or exergonic reactions is used to drive anabolic or endergonic reactions through an intermediate molecule, adenosine triphosphate. So this is where we get into what is ATP and why is it necessary. So energy is released from catabolic, so breaking down of molecules, and then with ATP, we begin to form anabolic reactions or endergonic reactions. So ATP is necessary for the entire metabolic process. So adenosine triphosphate allows the transfer of energy from exergonic to endergonic reactions. Without an adequate supply of ATP, muscular activity and muscle growth would not be possible. So we need ATP. We need adenosine triphosphate for everything that we do. And the breakdown of ATP also yields energy. So this is what this equation looks like. So in order to yield energy, ATP, adenosine triphosphate, with the enzyme called ATPase, which I will not quiz you on, but you might get quizzed on in another one of your class, is broken down into ADP, which stands for adenosine diphosphate. So ATP in the presence of ATPase is broken down to ADP, and this just means an inorganic phosphate, and then energy. So that yields energy when this is broken down. And then when it's rephosphorylated, so which means how does ADP turn into ATP? Well, it needs energy, and it needs an inorganic phosphate. And this is just the cycle. ATP is broken down to yield energy. Energy is used to reform ATP. Okay, so again, we need ATP for movement to happen. You need it. It's one of your basic energy sources. Now, there's 3 basic energy systems. And these exist in the muscle cells to replenish ATP. So basically, these exist so you are not constantly fatigued. So if you've ever exercised and you've become fatigued and then you regain your stamina after a rest period, you are replenishing ATP through one of these systems. And these 3 systems are the phosphagen system, the glycolytic system, and the oxidative system. Do I have a question? One sec. Yes, I can go a little bit slower. If you want to ask specifically which any questions that you have specifically. Also, I wouldn't worry. The big thing that you need to worry about right now, out of all of that, because that certainly is a lot of big words, what you need to know is that you need ATP for energy. Okay, so you need it. This is let's say that you ingested carbohydrates. Okay, you had, I don't know, a sweet potato or something like that. So that is, all right, let's see. Okay, so I'll just keep going with this example because that might help. So through an exergonic reaction, so a catabolic reaction, you are going to be breaking down that complex carbohydrate into things like glucose. So that's these smaller molecules, and that also yields energy. So that's why we eat food. We eat food to gain energy. And now We can also use that energy to create adenosine triphosphate, which is going to be necessary for everything that we do. So just the main thing right now is to understand that you need this molecule, adenosine triphosphate, to actually create movement. And then we'll get into the three basic energy systems. But I'm not, the big purpose of this class is not to make sure you understand cycles like this, but it's kind of necessary background information. Okay, I'll try to take it slow. Okay. So again, there's three basic energy systems that we use to replenish ATP. And the systems that we use are going to be dependent on the intensity and also the length of the activity that we're doing. So when I'm going out and running 10 miles, which I would not like to do, that's going to be a different energy system than if I was going out and doing a sprint and maybe doing that for 10 seconds. Now, at any given time, all three of these energy systems will be active, but the magnitude of contribution of each system to overall work is going to be dependent on that overall intensity of the activity. And we'll get into what that actually means. So if I was a marathon runner and I was competing in a marathon, I'm going to be using aerobic respiration, and that means I'm going to be using the oxidative system. Okay. That doesn't mean that the phosphagen system or the glycolytic system is not active, but the primary system that I'm going to rely on in order to actually make energy is going to be that oxidative system. If I was doing a quarter-mile run, I might be relying more on the glycolytic system, which actually has two subcomponents, which we'll get into. But if I was doing something like an Olympic lift, so if I was doing 1 or 2 repetitions of a heavy Olympic lift, I'm going to be relying primarily on what's called the phosphagen system. So we have different intensities of exercises, and depending on the intensity of the exercise, that's going to dictate which system you're going to be primarily using. So if we have a system, the phosphagen system, if we need energy or if we need ATP quickly, this is great. So this produces ATP very quickly. But its total ability to produce ATP is low. So we can produce it quickly, but we can't produce a lot of it. And in order to use this system, your body uses creatine phosphate and also previously stored ATP. So if you've ever asked anybody or if you've ever had anybody supplement with creatine, this is the system that they're seeking to help, is the phosphagen system. They're seeking to rapidly replenish energy in the phosphagen system. And we'll get more into all of these systems individually, but next is glycolysis. We can still produce ATP very quickly with glycolysis, but again, its ability to actually produce lots of ATP is low. And the energy that we use, the fuel that we actually use, is generally going to be blood glucose. Okay. And then the aerobic system. The aerobic system can produce a lot of ATP, but it's not quick. What do we primarily use when we're using the aerobic system when we're doing long distance exercises? Well, we still use blood glucose, but now we're also starting to tap into things like fat. So that would be a fuel that we would use if we were running more long distance. And again, it really all depends on the duration of the event. So if the duration of my event is 6 seconds long, I'm probably going to be relying primarily on the phosphagen system. Versus, again, if I'm doing a longer distance event, it's going to be the oxidative system that's going to play a bigger role. Okay, so let's actually start out with the phosphagen system. In the discussion of exercise-related bioenergetics, the term anaerobic and aerobic metabolism are often used. So what does that actually mean? So anaerobic just means it doesn't require oxygen, whereas aerobic mechanisms do depend on oxygen. Now the phosphagen system, in order to create energy, it does not depend on the use of oxygen. The phosphagen system provides ATP primarily for short-term, high-intensity activities and is active at the start of all exercise, regardless of intensity. So it is always the first thing that we use, but it doesn't necessarily mean it's going to be our predominant system for using energy. And it also, other than ATP, it relies on the breakdown of a phosphate molecule, which is called creatine phosphate, which again, this is why people supplement with creatine. If you look right here, creatine phosphate plus that ADP, creatine phosphate plus ADP can yield adenosine triphosphate. So again, creatine phosphate can be used to, it's called rephosphorylate ADP to create ATP. So again, if someone's supplementing with creatine, that's the reason why they're doing it. It's helping them create ATP. And because creatine phosphate is stored in relatively small amounts, the phosphagen system cannot be the primary supplier of energy for continuous long duration activities. So you have a limited store of creatine phosphate in your muscles. And that's none of that is ever going to be completely depleted, but it is going to be depleted with exercise, meaning you can't actually use it for long duration activities. So you're going to have to start relying on another energy source, which leads us into glycolysis. Okay, and again, don't the big things that I want you to take out of this are which system am I using depending on the intensity of exercise that's going on. You will most certainly learn about things like pyruvate in all of your other classes, but it's nice to get a primer on this right now. So when the breakdown of carbohydrates, so carbohydrates can either be glycogen, which is stored in the muscle. That's an option for what carbohydrates might be. Is delivered to the blood to resynthesize ATP. Now, the glycolytic system is not going to be as rapid as the phosphagen system, but its capacity is much higher due to a larger supply of glycogen and glucose compared to creatine phosphate. So in your body, you have a limited supply of creatine phosphate, but you actually have a lot more glycogen and glucose. The phosphagen system is, in other words, yeah, correct. Yep, that's correct, Gertie. All right, slideshow. Okay. Now, there are going to be two routes to which we can get energy out of glycolysis, and this depends on a molecule called pyruvate. Okay, so the end result of glycolysis may proceed in one of two directions. I will show you the actual graphical representation of this. Don't worry, I'm not going to quiz you on this in this class. So pyruvate can be converted to lactate, which can be used for energy right away, and it's fast. So ATP can be resynthesized faster, but it's also in limited duration. So this is actually what's called anaerobic glycolysis. So it's glycolysis where it doesn't need oxygen. Or pyruvate could be shuttled into the mitochondria, and the mitochondria does use oxygen. So this is what this looks like. Sadly, you probably will have to remember this graph in one of your classes. I remember when I was in XPhys, it was all about pyruvate. What happens to pyruvate in the citric acid cycle or the Krebs cycle? I'm not going to quiz you on this, but this is where we know if pyruvate moves into this cycle, we're going to start talking about the oxidative system. So the primary source of energy, ATP at rest, during low intensity activity is the oxidative system. And this usually primarily uses carbohydrates and fats as fuel. Okay, so this is the big thing that I want you to know. Exercise intensity and system use. I'm never going to quiz you on this graph. Okay. So the three energy systems, the phosphagen, the glycolytic, and oxidative energy systems differ in their ability to supply energy for activity of various intensities and durations. Phosphagen system's great for low duration, high intensity activities. The oxidative system is great for long duration, low intensity activities. And exercise intensity is defined as a level of muscular activity that can be quantified in terms of power output. Now, activities such as resistance training that are of high intensity and have high power output require a rapid rate of energy supplied and rely almost entirely on the energy supplied by the phosphagen system. So if you're doing a single set of something like a dumbbell press, you're relying on the phosphagen system for that single set, not for the entirety of the routine, but for that single set. Activities that are of low intensity but long duration require a large supply of energy and rely on the energy supplied by the oxidative system. So there's a big difference in terms of specificity for what energy system you're using when you're lifting weights and when you're doing a long jog. So this will be something that you should know. So the phosphagen system is number one for producing ATP quickly, but it's the slowest for its capacity to produce ATP. And intuitively, you all know this. Let's say that you can bench press 135 for 10 repetitions before you experience fatigue. Okay, well, why do you experience fatigue? You experience fatigue because you're running out of your fuel source, phosphagens. Okay. Fast glycolysis, that's going to be the second fastest for ATP production. Moving on down the line to oxidation of carbohydrates, and then eventually oxidation of fats and proteins. So we actually don't rely on the breakdown of protein too much until we've been exercising for a long period of time. Okay, fatigue and recovery. So energy substrates are molecules that provide starting materials for bioenergetic reactions, including phosphagens, which are that ATP and creatine phosphate, along with glucose, glycogen. So glycogen is just stored glucose in the muscle. Lactate, free fatty acids, and amino acids can be selectively depleted during the performance of activities of various intensities and durations. What this essentially means is that the energy that can be produced by these bioenergetic systems eventually gets reduced. So that's when you experience fatigue. So fatigue is experienced during many activities and is associated with the depletion, usually of two things, phosphagen and glycogen. So I've been competing in powerlifting for probably the last 10 years, and then I was challenged to run a half marathon, and I don't know why I did it, but I did it, and then I've been running ever since. And the fatigue that you experience with these two activities is going to be very different. Mile 7 of a race, I'm feeling fatigued because I'm depleted of glycogen in my muscles, versus the fatigue that I experience after 3 heavy lifts. That's going to be due to something different. I'm being depleted of my phosphagens. I'm being depleted of things like creatine phosphate. So the fatigue that I'm experiencing is happening for different reasons. So talking about depletion of phosphagen, so that would be something that you'd experience when you're lifting heavy weight or lifting weights for a shorter amount of time. So phosphagen concentrations in muscles are more rapidly depleted as a result of high intensity anaerobic exercise compared to aerobic exercise. Now this is interesting. So the stored so in your body, if you're not supplementing with creatine, you're at probably something around like 70% of maximum capacity. So if people supplement with creatine to increase that up to 100%. And now creatine phosphate can be decreased quickly, so a lot, 50 to 70% during the first stage, so even the 5 to 30 seconds of high intensity exercise, and can be almost eliminated as a result of very intense exercise to exhaustion. Luckily, this can be rapidly restored as well with rest. ATP concentrations may decrease up to 50 to 60%, but complete resynthesis of ATP can occur within 3 to 5 minutes, and complete creatine phosphate resynthesis can occur within 8 minutes. So if you've ever lifted anything really heavy for 2 or 3 reps, and then you're resting for 3 to 5 minutes afterwards, that's probably necessary because you need to resynthesize ATP within your muscles to continue to do that kind of work output. Now, limited glycogen stores are available for exercise. It's going to be a lot more than creatine phosphate. So we have about 300 to 400 grams stored in the muscle at any given time. Glycogen is also stored in your liver. And the rate of glycogen depletion is related to exercise intensity. So if we want to break down glycogen, again, that's that catabolic reaction that happens with what's called, I'm not going to quiz you on this either, but glycogenolysis. So that's when we break down glycogen to become glucose. So glucose is just blood sugar. At relative intensities of exercise above 60% of maximal oxygen uptake, muscle glycogen becomes an increasingly important substrate. And also, and again, if we're doing a single set of resistance training, that's probably going to reduce our phosphagens, our creatine phosphate. But very high intensity intermittent exercise, such as resistance training, also can cause substantial depletion of muscle glycogen. So basically, although phosphagens may be the primary limiting factor during resistance training, with few repetitions or few sets, muscle glycogen may be the limiting factor for resistance training with many total sets and larger total amounts of work. Now my slide doesn't want to change. Okay, there we go. Okay, metabolic specificity of training. So appropriate exercise intensity and rest intervals can permit the selection of specific energy systems during training for specific reasons. There's different ways that we can train to emphasize different bioenergetic adaptations. So one that you've probably heard of or done before is interval training, and it's a method that emphasizes bioenergetic adaptations for a more efficient transfer of energy within the metabolic pathways by using predetermined intervals of exercise and rest periods. So that might be, I'll give you an example, but there in a second, but something like a quarter-mile repeat or sprints with specific rest periods in between. That can be interval training. Now, knowledge of the time intervals and recovery periods for each of these energy systems is critical to maximizing the amount of work that can be accomplished for a given exercise intensity. So if you know that it takes 3 to 5 minutes to restore phosphagens, so like creatine phosphate and ATP, for a resistance training protocol where you're going relatively heavy and you don't give yourself sufficient rest, you're not really maximizing the specificity of your training. So you want to know what system you're using, how long it takes for you to recover the energy that you need to actually continue doing work. So if the exercise that I was doing primarily relied on the phosphagen system and it lasted 10 seconds or something like that, you might want to allocate the appropriate work to rest ratios. And when I think about this, I'm thinking more in terms of sprinting. If I was using the oxidative system, so I'll give you examples here. If I was doing something like a quarter-mile repeat, which could take 90 seconds, something like that, I might end up using a 1 to 3 work to rest ratio. So let's say a 1 to 3 work to rest ratio just means if it took me 90 seconds to get the work done, I would go times 3, so 270 seconds before I did it again. Versus a half-mile repeat, which would be something that's a little bit lower intensity. So that would be I run a half mile, I rest, run another half mile. So something like that, I might use a 1-to-1. So in that case, it might be like 3 minutes on, 3 minutes off. Okay, and then combination training. How should we use it? How would we use it? So combination training would be combining aerobic training with muscular strength or muscular endurance training. So aerobic endurance training added to the training of anaerobic athletes to enhance recovery is a common approach that people have used So the idea there is that if you build up an aerobic base, even if you are an anaerobic athlete, that can help you actually recover. On the other hand, is combining aerobics may reduce maximum strength and muscle growth. So what that means is if you're trying to concurrently do aerobic training and muscular strength training or training for muscular growth, that aerobic training might interfere with muscular growth or muscular strength demands. There are some metabolic reasons why that may happen, but primarily it might also just impede with your ability to recover. Okay, I know that probably was a lot. Here's the big thing that I want you to know. I want to exit out of this. Understand, if I'm doing exercise for a specific amount of time, what energy system am I using? And then, does that make sense for what my goals are? And I think a lot of you probably already intuitively know this. If I said, I want to increase muscular size, like I want to get bigger muscles. Okay, what do I do? How do I put that together? What's the time interval for work that I should be doing, and how can I optimize recovery as well? Or if I said if I want to improve my muscular endurance, okay, well, if I want to improve my muscular, or let's just say I want to improve my aerobic endurance, sorry, you're not going to put me out doing 10-second sprints. That's not going to work for that goal. This is specificity. So one component of specificity is just, am I using the metabolic system that's specific to the goal that I have? Other training principles that we're going to go over after you take your little quiz is going to be individualization, progressive overload, and then also variation. And what we're also going to cover after you do your quiz, we'll cover the quiz, is going to be specific training variables. So what I want you to do is I want you to log on to Blackboard, and I think it's only 3 or 4 questions for the quiz that relates to what we just covered. And I'll give you 6 minutes to finish that, and then we'll review the answers, and then we'll move on to the next lecture, okay? So you take that quiz, and then any questions that you might have, let's cover that. I'm going to pause this lecture, and I'm going to upload.